There's a nuclear fusion reactor hovering 150 million kilometers above our heads. It is effectively infinite, and it is relentlessly bombarding Earth with energy. In a single hour, the Sun strikes our planet with enough photons to power our entire global civilization for a full year. That is the scale of the resource we are dealing with. Yet for the last 70 years, our ability to capture this bounty has been throttled by a fundamental law of physics, known as the Shockley-Queisser limit. This is the theoretical ceiling that dictates conventional silicon solar cells. The blue panels you see on rooftops everywhere can convert, at best, about 33% of incoming sunlight into electricity. The rest is lost, mostly dissipated as waste heat. For half a century, we accepted this 33% figure as the speed limit of solar energy. We treated it as an immutable law of nature. But recently, a quiet revolution has been brewing in the quantum realm that challenges this assumption. It does not involve building physically larger panels or covering more deserts in glass. Instead, it involves engineering the very heartbeat of a solar cell, a quasi-particle known as the exciton. By marrying the flexibility of organic molecules with the raw conductive power of inorganic semiconductors, scientists have unlocked a new state of matter called hybrid excitons. Combined with the quantum mechanics of organic quantum states, specifically a process called singlet fission, this technology promises to shatter the old efficiency limits, turning what was once waste heat into usable electricity, and ushering in a new era of hyper-efficient solar technology. To understand why this is happening now, and why it changes everything, we have to look at the limitations of the incumbent king of solar power, silicon. Silicon is the workhorse of the electronics world, but when it comes to light, it has a personality problem. In a standard silicon cell, electricity is generated when a photon, a particle of light, strikes the material. If that photon has enough energy, it knocks an electron loose from its atomic orbit, leaving behind a positively charged vacancy called a hole. This electron and this hole are momentarily attracted to each other by electrostatic forces, forming a bound pair. This pair is what we call an exciton. The entire goal of a solar cell is to break this couple up, to rip the electron away from the hole before they can snap back together and neutralize each other. If you separate them, you get current. If they recombine, you get nothing but a tiny vibration of heat. The problem with silicon is the Goldilocks dilemma. Silicon has a specific band gap, which is the minimum amount of energy required to knock that electron loose. If a photon from the sun has too little energy, like infrared light, it passes right through the panel as if it weren't there. If the photon has too much energy, like ultraviolet or blue light, the silicon absorbs it, but it creates an electron with too much excitement. That extra energy doesn't go into the wire. It is instantly shed as heat within the crystal lattice. This brings us to the most frustrating rule of conventional solar physics, the one-to-one rule. No matter how energetic a photon is, in silicon it generally creates only one electron-hole pair. 1 unit of light in, 1 unit of current out. The excess energy of a powerful UV photon is simply thrown away. This is where that 33% limit comes from. We are essentially ignoring the high-energy portion of the solar spectrum. To break this limit, we needed a material that could multitask. We needed something that acts like a highway for electrons but also acts like a sponge for light. Materials science has traditionally been divided into two distinct camps. On one side, you have inorganics. These are materials like silicon, gallium arsenide, or the newer 2D transition metal dichalcogenides like tungsten diselenide. Think of these as the highways. They are rigid, highly ordered crystalline structures that are excellent at transporting electrons quickly over long distances. On the other side, you have organics. These are carbon-based polymers and small molecules. Think of these as sponges. They are soft, flexible, and chemically tunable. While they are generally terrible at moving electricity efficiently compared to silicon, they have unique quantum properties that allow them to interact with light in exotic ways. For years, researchers tried to simply mash these two together, hoping to get the best of both worlds. But the interface, the boundary where the organic sponge meets the inorganic highway, was always a chaotic mess. Electrons would get stuck at the border, or energy would be lost trying to jump the gap. That changed in late 2024 and throughout 2025. Researchers, utilizing advanced momentum microscopy, revealed a stunning phenomenon when these materials are layered with atomic precision. When you place a single sheet of a 2D inorganic semiconductor, like tungsten diselenide, against a specific organic coating, the excitons don't just sit on one side or the other. They hybridize. A hybrid exciton is a quantum state where the electron resides in the inorganic layer, the highway, while its partner, the hole, resides in the organic layer, the sponge. Even though they are in different materials, they remain bound together by quantum forces across the interface, moving as a single entity. This is critical for two reasons. First, the transfer of energy between these layers happens in femtoseconds. A femtosecond is 1/4 of a second. This transfer is so fast that it beats the process of thermalization. It moves the energy before the material has time to waste it as heat. Second, and perhaps more importantly, this structure allows us to access organic quantum states. This is where the physics gets truly weird and where the efficiency gains come from. In the quantum world of organic molecules, energy states come in different flavors, primarily singlets and triplets. A singlet state is the standard excited state created when light hits a molecule. It is bright, but short-lived. A triplet state is a dark state. It is long-lived, but usually it is very hard to access directly with sunlight because of spin conservation rules. In standard solar physics, triplets are a nuisance. They trap energy until it dies out. But in these new hybrid systems, we can exploit a process called singlet fission. Singlet fission is the solar equivalent of buy one, get one free. In specific organic materials, like pentacene or tetracene, when a high-energy blue photon hits the molecule, it creates a high-energy singlet exciton. But instead of decaying and giving us one electron, this singlet creates a quantum superposition that splits itself into two triplet excitons, each carrying half the energy. In a standard silicon cell, a blue photon gives you one electron. In a singlet fission hybrid cell, a blue photon gives you two electrons. This process effectively doubles the current generated from the high-energy part of the solar spectrum. By placing a singlet fission layer on top of a standard inorganic cell, we can boost the theoretical efficiency limit from 33% to over 45%. This is a massive jump. It turns the waste heat from blue and UV light into usable electricity. But the magic doesn't stop there. We also have to talk about the dark energy reservoir. As I mentioned, triplet excitons were historically considered dark states because they don't emit light and are hard to harvest. They just sit there. However, the new hybrid architecture changes this dynamic completely. The inorganic 2D layer acts as a perfect drain for these dark states. The hybrid exciton state acts as a bridge, allowing the energy stored in these long-lived organic triplets to flow effortlessly into the inorganic semiconductor where it can be collected as electricity. We are essentially tapping into a reservoir of energy that was previously invisible to our solar panels. So what does this look like in the real world? How do we move from a femtosecond laser lab to a power plant? The first generation of this technology will likely appear as tandem cells. Imagine a standard silicon wafer, but coated with a nanometer-thin layer of these organic-inorganic hybrids. This coating would absorb the high-energy blue and UV light, perform singlet fission to double the electrons, and let the lower-energy red and infrared light pass through to the silicon underneath to be harvested normally. It is a dual-engine approach, but the future applications are far more radical. Because hybrid excitons can be chemically tuned to absorb only specific wavelengths, we can design panels that are transparent to visible light, but absorb UV and infrared. This creates the possibility of transparent solar windows. Skyscrapers could essentially become massive, invisible power plants, harvesting the energy that currently just heats up the office. Furthermore, the organic component makes these materials flexible. We are looking at solar skins, bendable, printable solar paint that could coat electric cars, constantly recharging the battery using these high-efficiency quantum states. There is also the advantage of low-light performance. Because the dark triplet states are incredibly long-lived, the charge carriers stick around longer than they do in silicon. This potentially allows these panels to harvest energy more effectively in diffuse light, during dawn, dusk, or cloudy days, smoothing out the intermittency problems of current solar tech. Of course, we must address the challenges. This is not a done deal. The biggest hurdle is the interface problem. Creating a perfect contact between organic and inorganic layers requires atomic precision. A single speck of dust, a bubble of air, or a molecular misalignment acts like a roadblock, killing the quantum state and ruining the efficiency. We can do this in a vacuum chamber, but doing it in a factory is a different beast. Then there is the issue of stability. Organic molecules are notorious for degrading. Think of how plastic fades in the sun. The very UV light we are trying to harvest destroys organic bonds over time. Oxygen and moisture are also enemies. Engineers are currently racing to develop encapsulation barriers, basically molecular shrink wrap, that can protect these delicate quantum states for 25 years or more, which is the industry standard for solar panels. And finally, scalability. We are talking about materials that are often just a few atoms thick. Printing them by the square kilometer at a cost that competes with dirt-cheap silicon is the next great engineering challenge. However, despite these hurdles, the trajectory is clear. We are standing on the precipice of a shift in how we generate power. For decades, we treated sunlight as a bulk commodity. We dumped photons into silicon buckets and hoped for the best, accepting the waste as a necessary cost. Hybrid excitons and organic quantum states represent a shift to precision energy engineering. By manipulating individual quantum states, splitting photons, and harnessing the unique dance of electrons at the atomic interface, we aren't just improving solar power, we are redefining its physical limits. The sun has always been the ultimate power source. Now, thanks to the marriage of organic chemistry and quantum physics, we are finally building a bucket big enough and smart enough to catch it all.